Hi everyone. So now we're going to do the second part in which we're going to make ourselves an electromagnet. And we're going to look at the properties of the electromagnets that we're going to make and then compare them, at least qualitatively, in terms of how much stuff they can pick up and kind of determine the strength of that magnetic field that's sort of made by how much or how many things that this electromagnet can pick up in, say, like a chain of stuff. So, say if you have something like you're going to pick up some paper clips. How many paper clips did it pick up in sort of a chain? If you connect them like this, in that sense, did the electromagnet pick up through that? That can kind of help determine the electromagnetic strength that's produced by our electromagnet. So the things that you'll need for today's experiment and something that you can look into, in addition to not only differences in the types of wires you might use, you may also look at the differences in the spacing of the wires themselves as well, and determine a few qualitative results from that, and then make yourself a little report on that for that matter. So things you'll need, definitely wire. Preferably if you can get a hold of at least a nice chunk of wire such that you can do quite a bit of wrapping of the wire around whatever core we're going to be using for today. So I recommend using an iron-based core. So basically grab yourself some a nail, or you can always use say a bolt or something like that. The nice thing about the bolt is that the bolt has this threading already that can kind of help guide with twisting the wire onto the bolt itself, whereas with the nail it may require a little bit more finesse in trying to coil that around in order for us to make our solenoids so that we can test that. So later on, I'll in a demo, like I said before, I'll look at how this acts as a transformer and creates a voltage when a change in the magnetic field or the magnetic flux. In our case, this would just be the magnetic field would be changing in this particular transformer based on the change of the current that's going through either of these coils at any given time, and that the other coil that would not be attached to the primary supply of current will have an induced current or an induced voltage that will then be measured by, say, a voltmeter or something. So that's kind of something to look at a little bit later as an application for electromagnets that we might produce in today's lab. So what you'll need, as I said again, core, something to pick up, something iron-based. So again, our zinc-coated paper clips usually have an iron core to them already. You can always use staples. Just punch out a bunch of staples from a standard stapler. Use that if you have access to iron filings, so I don't recommend that you go out and buy them just specifically for this. I may actually demonstrate some of the curvature of the magnetic field that's produced by some of these electromagnets by using some iron filings on top of a white sheet of paper, so that you kind of get an idea of what that magnetic field will kind of look like produced by, say, a solenoid in that instance. Unfortunately, we won't be able to look inside the solenoid. That was actually supposed to be a different lab that we were supposed to do, but this is as good as it's going to get. So the other thing that you'll need is some power source. So I do recommend getting a conventional battery if you have not been able to get a homemade battery to produce enough current. that's something that you'll need, either any of the standard AA, AAA, up to D cell batteries, or you can use standard 9 volt battery, which may be a little bit easier to try and connect your electromagnet to, rather than trying to jerry-rig something like what I did here to try and connect say the ends and keep things in place while I'm playing around with the electromagnet as it's hooked up to the battery. So just optional things, you may need some extra wire to kind of make something that looks like this to hold a battery in place so it doesn't roll around, or as well as making connectors so we can connect it and make ourselves a magnet. Alright, so so those are optional things. You may need like some sort of cutting device in order to make the holes in the cardboard and stuff like that, and some sort of puncturing device. You can certainly just use, you know, paper clips to MacGyver that puncturing device, and then thread the wire through if you need to do that as well. So just, again, play around. There's no right or wrong way to do any of this stuff. Well, I guess there is a wrong way to do it, but in terms of how good it is, not particularly you know, anal about that. So I'm not asking for pristine wraps or anything like that, or coils and things like that. So just it is what it is, and just do the best you can with what you have. So let's begin. So like I said, what we'll need, in addition to the wire that you're going to need, you're also going to need something that will cut the wire and strip the wire as well. So again, you may need something like needle nose pliers or wire cutter, and then at least for I've been usually using the scissors to help strip the wires without fully cutting into the wire too much. I think it actually helps a little bit easier in stripping the wire. It just will cut through the plastic and not fully through the wire itself, making that stripping much easier. So you'll need a nice long thread of wire in order to accomplish this, depending on the length and the diameter of the core that you're using. Certainly it does not have to be cylindrical in nature for your core. If you so happen to have, I don't know, a rectangular prism of iron, an iron bar or something like that, that'll work just fine as well, so long as what we're going to do is just coil it around. And so you'll just take your time patiently just coiling this around and around and around until you get to some sort of end point in which you've essentially, however you feel that has been accomplished. You know, it doesn't have to take the entire length. It can be somewhat short, it can be somewhat long. Here I have an example of a short one somewhere on a iron core like this, so you don't have to necessarily go the entire length like I did with this nail, but you know, something to that effect for the experiment, just so that you get a sufficiently long enough solenoid that's produced, that we can then produce a good enough magnetic field inside the core that will then be attractive to our metallic objects. Alright, so once you have that completed, and you may need some tape optionally in case the wire isn't setting quite nicely, as say here, where the wire with a bit thicker gauge can actually stay in place much more nicely than thinner wires will. So we'll test this out, and then I will remove this one, and then we'll test out this particular one, which has a much wider spacing between the wires, but it also has a thicker gauged wire between this and this. So if I try and get that as close as I can, kind of see at least apples to apples, that definitely this has more coils per unit length versus this, and that they both have different gauges in that sense. So, which I can show with these wires if I put them up close together, so you can kind of see a little bit apples to apples. Well, if I don't jiggle that around too much, but these are also little wires that I've kind of twisted together, so depending on how that operates for us, we'll see whether or not we can get it to work to a level in which it can pick stuff up. Alright, so I'm going to use my little jerry-rigged battery placer, and then just kind of put this in, see if it's making connection everywhere, and it looks like it is. So I'm just going to loop these through, make a connection like such. Oops. Alright, something like that. Alright, and let's see if it will pick something up. Wow, there we go. It's almost trying to. Oh, almost had it. Alright, so that's something that you can play around with a little bit. What you'll also notice is that if I unhook this completely, like this, without any connection to the battery itself, you may actually find that it has a bit of a residual magnetic pull to it. And this is what is called hysteresis. And it's a property of objects that undergo a strong magnetic field. And basically what will happen is that basically what you have is the electrons that surround the core of the atom itself, these valence electrons, they already produce a magnetic field inside, based on the fact that the electron is spinning. So this is a charge that's moving, so this creates a current, and this current will then therefore make a magnetic field. These magnetic fields generally for many objects are randomly oriented, which basically negates the effect of any sort of particular direction in which the magnetic field would be going. So in this case what we have is iron, has a few valence electrons, so it would be strongly moved in that sense if a magnetic field is present. An external magnetic field is present, and what will happen is that all those random orientations will start to align and fix to that orientation of the external magnetic field. Right? This is basically how the fact that the core works in these electromagnets is that the core itself is becoming magnetized in that sense, based on the external magnetic field that's produced by the solenoid wire and the power supply from the battery. The residual effect is effectively coming from the fact that after you unhook it, these random orientations of the atoms don't necessarily go back instantaneously to their random orientations. They take a little bit of time to do that, and so it takes a bit of time for it to eventually settle back down into a randomized orientation, and this is what is called hysteresis in that essence. And so you can effectively have a little bit of magnetism left over inside the core itself based on that. It's obviously going to be weaker without the external magnetic field being supplied to the core, but eventually what will happen is it will taper off eventually to zero. In fact, usually in hysteresis curves, what will happen is it will actually go back below zero or at least in terms of alternating currents, you can have a magnetic field that alternates like this, and it can also, I believe it can also alternate a little bit in that sense, but something to look into if you're interested in discussing that as well. Sort of also the basis upon which nuclear magnetic resonance works, except instead of electrons that you're aligning with the magnetic field, you're using nucleons and the nucleus itself. So you need to have nuclei that have basically a half-integer spin, total half-integer spin. The spin kind of acts like a charge that's moving as well, which will produce a current, effectively in some sense, in a magnetic field from that. So if you have basically, in that instance, it's say if you have two nucleons, spin up, spin down, their magnetic fields are going to cancel effectively. Whereas if you just have one, or you have, one up, one down, and then another one that's up, you effectively have spin up as the total magnetic, or this total spin of the nucleon itself, and therefore you can get this sort of resonance as it sort of cycles down, and using radio waves to kind of look at that sort of relaxation of those nuclei coming back into their random orientation inside whatever specimen that you're looking at, whether it be a human for the case of MRIs, or for crystalline samples that you might have at a national lab, that you would kind of look at the sort of overall crystalline structure in that. So you kind of have to be aware of some of those things. Not all things are affected by magnetism, or at least it might need a very, very, very strong magnet in order to accomplish certain things. So things like iron, cobalt, nickel, these are what are termed as ferromagnets. So these can be actually naturally found as in nature, having the effect of basically a magnet, and they have domains in which there is a general alignment of these valence electrons in their orbitals spinning around, creating this magnetic field that I was describing with the hysteresis curve. Okay, so essentially these are set after heating and being exposed to an external magnetic field. That's basically how you would make a permanent magnet, is by essentially heating up, say, this iron core, so that the metal is no longer in a crystalline form. It's starting to not bind itself in such a way. And so then you apply an external magnet to that. All of them will, or many of them will start to align in that particular direction, and then you cool it, keeping the magnetic field on, and then as it cools, the iron or cobalt or nickel will eventually come back into its crystalline form, and in that instance, that's where you create these domains in which there will be preferential alignment towards a particular direction for the magnetic field overall in that particular section of the crystal. So something to think about. Now, after that little bit of a aside, I will come back in just a moment to put on the other electromagnet, the one that we're going to test out and see how that fared in comparison to this one, and we'll conclude with that, and then the following video should just be a demo on the transformer as promised. So okay, so now I have the other electromagnet, the other solenoid, put onto the same iron core, in this case our nail. I'm going to attach it just like we did before, and we'll see what sort of level of picking up power we can do with this particular electromagnet. Okay. Fix this here, here. Oh goodness. Something like that, maybe. Okay. Oops. Disconnected, so sometimes my things don't quite work out the way that I wish them to. Pretty much how all science works. Maybe I'm just gonna have to grin and bear it and just touch them. There we go. Okay, I'm just gonna have to do that. Give me a second. Here, let's do this. There, try that. Oops, that worked. Come on. There we go. Something like that. There we go. Aha! Seem to be getting a little bit more. Oh, seems like this one's a little bit more powerful. Okay, and we'll kind of talk about what may be making it more powerful than the other one, even though we might expect the other one to be more powerful. Maybe we weren't, but we can certainly look at the relationship of solenoids and the magnetic field that's produced by solenoids themselves. Here, you have we'll have our relationship of B being, oh goodness, let me go grab. Okay, so I grabbed a marker and it seems to look okay right now. So here's the relationship that we have for the magnetic field for a solenoid. This is derived from Ampere's law. Maybe you might have done that in class already. I won't go into detail on how it's derived here, but I'll just kind of go over some of the implications of it for at least what we're doing here. So the magnetic field that's produced inside the solenoid itself is related to the permeability of free space, it's mu naught, times little n, which we'll find out is basically this unit number of turns per unit length. And basically it's calculated by taking the total number of turns in the solenoid itself and dividing it by the total length, and usually this is in turns per meter. Turns is kind of a superfluous unit that really doesn't kind of factor into the total unit conversion and all that sort of stuff. It's kind of a pseudo unit in that it just kind of describes at least what we may be talking about. And then naturally current. So we have some sort of current, some flow of charges that's producing this magnetic field that we're seeing here. So you'll see here that this solenoid is not dependent upon anything related to the diameter of the coil itself or of the wire itself, and this is just assuming essentially to an approximation that this is a perfect solenoid. It's infinitely long, and that there aren't any fringe effects or anything going on like that. So that's something to be aware of in that case, whereas we're working here with real solenoids, this relationship may not necessarily be accurate. So there may be a little bit of error associated with that. So just be aware of that. And here again, I've reiterated what the permeability of free space is. Again, it's 4 pi times 10 to the minus 7 Tesla meters per amp. All right. So that's that value. It's a constant. That's found from, I believe, Gauss's law or something to that effect. So something to look into as well. So what may be causing the fact that the magnetic field is stronger for the lower end solenoid than the higher end solenoid? So we had, in the first part, we had a solenoid that had a very large little n. So basically it had a large total number of turns per the total length. These are about the same length in total, but we found, at least hopefully we saw, that there were obviously more turns in the first solenoid versus the second. But why should we believe, at least if we knew this beforehand going into this, why it was weaker than this one in the end? And it might have to do with the current itself, and we can measure the current that flows through both of them, and we might find that the one with the larger N probably had very, very, very small current in the overall system. So that's probably what was going on in that sense, and then we had more current flowing in this particular sense. So kind of wasn't a one-to-one sort of relationship that we would want to expect to see, but certainly if you're wanting to look at the dependency of little n as a function of B, one thing that you can do, I would recommend using the same type of wire and then just kind of spacing it out, making sure that that spacing is uniform throughout, not that so that it's that you basically get a nice uniform little n throughout your solenoid. And then again, using the same wire hopefully will give us the same current that's flowing through everything for our case. Okay, so that's just something to consider when you're looking at these electromagnet and kind of how those things are doing. So your qualitative data may include like how many, like I showed before, how many paper clips you were able to pick up with just a single electromagnet, and just kind of chaining them together and seeing how that sort of plays out in the end. Okay, so certainly there's not going to be any quantitative analysis of this relationship, but hopefully we can see some sort of qualitative relationship, particularly if we use sort of the same type of wire and allow it to vary in that sort of sense. Certainly you can always try and hook up more batteries. Maybe that will give a bigger eye as well. So certainly you can always try that. Certainly more power will probably bring more ability to actually pick up things. So certainly that's another option to do in order to increase I. Whether or not you can actually figure out what I is, or well, we can figure out what N is. Hopefully you guys have access to a simple ruler to kind of measure that if you want to in that instance. But for the current, don't worry too much about it. Hopefully you'll see a stark difference between using one battery versus 3 batteries or something like that. And it may even be a linear relationship that you might add more batteries, the longer the chain that you can produce in that particular instance is. So go ahead, try something out. Again, if you're having difficulty acquiring any of the materials, please don't hesitate to email me or ask me questions. I can certainly send as much material as I can via standard mail, so just be aware of that. Certainly, I don't want to get a call from the FBI. You know, what am I doing sending wires to all sorts of people all over the country during this time? So just be aware of that, I guess. Hopefully that doesn't happen, but I'm more than willing to have that happen if it means you guys getting the education that you guys need in order to be fully fledged scientists. So without much more to say about this, just have a good time with this. Again, try not to worry too much about this. I'm trying to make this low stress for the most part, so try not to get all hyped up about things and afraid that you're going to do something wrong, because that's part of what science is figuring out what we did wrong and then attempting to correct for that, and then hopefully in that process discover something, and to not be too sappy about it, something about ourselves as well. So that's just something to sort of motivate you guys to kind of, do things. You don't necessarily have to do everything in the lab. There's always something that can always be done outside a lab that is just as equally fun, if not equally dangerous. So there is that. So please go ahead and look that over. Before I go, I just reminded myself that I also wanted to show you guys how the magnetic field would look under iron filings, so I'm going to do that really quick and hopefully not take too much more of your time. So give me 1 second. Okay, and we're back. So here underneath this white sheet of paper, I hopefully have the electromagnet running, hooked up to a C-cell battery. Maybe I'll need to make sure that that's fully hooked up, producing, oh, there it goes. Oh, I just need to make sure everything's connected nicely, and let's just sprinkle a little bit on. Here we go. So you can kind of see here, at least at this point in this region here, this is one end of the electromagnet. You can kind of see how the iron filings kind of deviate a little bit in a sort of wrapping effect. Here's the other one. Maybe you can kind of see that the magnet producing some of the iron filings are, my pencil is steel, so it's going to be a little magnetic in nature, so you can kind of see that the iron filings are kind of flowering out from that region too, and then also deviating in that sense as well. Here in this region, we're not really seeing a lot. Technically, if we took the solenoid to infinite length, we would effectively see what we see out here in the very, very edges is that, ooh, there we go. That's nice. That looks really nice. So basically right now we're just seeing some fringe effects outside the solenoid itself. So basically the solenoid itself is what inside is where the magnetic field is being produced, not outside, like you would expect from like a permanent magnet or something to that effect. So here we're seeing a nice display, and then those magnetic fields are kind of wrapping back in on themselves from end to end, as all magnets do. There are no monopoles. At the very minimum, we've only observed dipoles. So in this instance, there's basically a positive end and a negative end to that polarity in that sense. And you can have multiples as well, so you can have quadrupoles and octupoles and all that sort of stuff, and so on and so forth. But at least at this time, we have not experimentally or observed a monopole for magnetic charge, if you will, at this point in the game, though there are some experiments out there trying to desperately look for that, either galactically or in high energy physics, like at LHC, CERN, or at Fermilab. It's something else to be excited about if you're interested in those sorts of discussions as well. So hopefully you enjoyed this. Again, don't hesitate to ask questions or comment or anything like that to me at any time throughout the rest of the semester. So stay safe, and I'll see you guys and talk to you later.